You want your kid to learn real coding skills, but handing them a tablet at age 4? That doesn't sit right. And honestly, it shouldn't. There's a smarter way to build those skills, step by tactile step, without a screen in sight until they're actually ready for one. I'm Dr. Priya Mehta, and I've mapped out the exact progression that takes a preschooler from pushing buttons on a toy robot all the way to writing industry-standard Arduino code in C++. You're listening to the STEM Lab podcast. Quick heads up before we dive in, everything you're about to hear, the research, the data, the actual script, all of it was written and verified by real people who know this stuff inside and out. The voice you're hearing right now, that's AI generated, which lets us get these episodes out to you faster without compromising the quality of the information. Just wanted to be upfront about that. Now, if you've been listening for a while, thank you. It means a lot that you keep coming back. And if this is your first episode, welcome. Glad to have you here. We drop new episodes every Monday, Wednesday, and Friday, always focused on practical STEM guidance you can actually use. Today, we're walking through a complete progression from screen-free coding tools all the way to Arduino programming. So let's jump in. This guide is for parents who see coding as a skill-building investment, not entertainment. I'll show you how to move through each phase with intention, building computational thinking before your child ever touches a keyboard. Let's start with the foundation stage, ages 3 to 6. This is all about building sequencing and cause-effect logic. Before your child can write a single line of code, they need to internalize sequencing, directionality, and cause-and-effect reasoning. These are the cognitive building blocks that make programming intuitive later. Screen-free tools at this stage use physical manipulation, moving pieces, following paths, arranging cards to make abstract logic tangible. Robot toys with directional buttons work beautifully for ages 3 to 5. Check the link below to see the current price for the Learning Resources Code & Go Robot Mouse Activity Set. Your child presses forward, right, forward, and watches the mouse execute the sequence, building immediate cause-effect feedback without text or symbols. Sequence cards and storyboarding kits come next, usually around ages 4 to 6. Tools like ThinkFun Codemaster programming game introduce algorithm design through puzzle cards. Kids arrange instruction cards to solve a maze, learning that order matters and debugging is part of the process. Core programming concepts delivered through cardstock. Unplugged board games that teach conditionals fit the 5 to 6 age range well. Games like Robot Turtles teach if-then logic. If there's a wall, use the laser card without any electronics. This is where your child starts understanding conditionals, the foundation for all branching logic in real code. There's an observational skill you can build here too, something I call chunking complex tasks into steps. At this stage, verbalize sequencing in daily routines. First, we put on socks, then shoes. What happens if we reverse that? This cognitive habit, breaking tasks into ordered steps, is algorithm thinking in its purest form. Pattern recognition activities work great for ages 4 to 6. Physical pattern blocks, sequence puzzles, and even clapping games build loop recognition. When your child notices this part repeats 3 times, they're identifying loops. They just don't call them that yet. Spatial reasoning through directional play matters for ages 3 to 5. Grid-based games where kids move pieces up, down, left, right mirror how code controls motion on a screen or a robot on a floor. Products with physical grids like unplugged coding mats let kids internalize coordinate systems through their bodies, not abstraction. By the end of this stage, your child should be able to create a multi-step sequence to achieve a goal, recognize when the sequence fails, that's debugging, and revise it independently. They don't need to know the word algorithm, but they should understand that instructions have an order and consequences. On the practical side, there's no power requirements here. All materials should be drop-proof and toddler-safe. No small batteries or choking hazards. Look for kits that store flat or in small bins. Durability for repeated use matters more than variety at this stage. For a deeper look at how to evaluate these tools for longevity and developmental fit, I've got a screen-free coding kit evaluation checklist linked in the resources. Now, let's move to the intermediate stage, ages 6 to 9. This is where we introduce functions, loops, and debugging without syntax. Once sequencing feels intuitive, your child is ready for abstraction, using symbols to represent actions, nesting instructions, and understanding that one block can contain multiple steps. This is where the progression bridges concrete manipulation and representational thinking. Card-based coding systems with function cards fit ages 6 to 8. Kits like the Osmo Coding Starter Kit for iPad, used without the screen component in some activities, or purely unplugged equivalents use cards to represent functions, reusable chunks of code. Your child learns that jump can mean move forward twice, then up once, teaching abstraction and efficiency. Physical programming boards with loops and conditionals work for ages 7 to 9. Products like the Code and Go Robot Mouse Advanced sets introduce loop tiles and conditional switches. Your child programs the robot to repeat this path 3 times, or if sensor detects obstacle, turn right, mirroring for loops and if statements in real code. Collaborative unplugged coding games are great for ages 6 to 9. Games where one child writes instructions and another executes them, human-robot activities, teach communication precision. When your child's instructions fail because they weren't specific enough, they experience what programmers call semantic errors without the frustration of a screen. Debugging challenges with intentional errors fit the 7 to 9 range. Kits or worksheets that present a broken sequence and ask what went wrong build critical debugging skills. This is where your child learns that errors aren't failures, they're information. That mindset shift is essential before transitioning to text-based code. Pattern abstraction and nested loops come in around ages 8 to 9. Activities that require recognizing this 3-step pattern repeats inside this 5-step pattern teach nested loops. Physical manipulatives make this visible in a way that screen-based block code sometimes obscures. Binary logic games and sorting algorithms also land around ages 8 to 9. Unplugged games that teach how computers sort information, like card sorting challenges, introduce algorithmic efficiency. Your child starts thinking about better versus worse ways to solve a problem, the heart of computational thinking. Your child should be able to design a multi-step program using reusable functions by the end of this stage, recognize and fix logic errors independently, and explain why a sequence works or doesn't. They're ready for visual block-based coding when they can abstract a physical sequence into symbolic representation without needing the physical objects present. Most products still require no power here. Look for modular systems that expand, additional cards, tiles, or challenge packs, rather than single-use kits. Durability focus should be on laminated cards, sturdy tiles that won't warp, and storage solutions that keep pieces organized through dozens of uses. For guidance on when your child is ready to move from these tools to screen-based platforms, there's a guide on transitioning from screen-free coding to Scratch and Python programming linked below. Next up is the transition stage, ages 9 to 11. This is block-based visual programming with hardware control. This is where the progression meets the screen, but not passively. Your child uses visual block-based languages like Scratch, Blockly, or MakeCode to control physical hardware. The tactile feedback loop remains. They write code and a robot moves or a light blinks. This bridges the abstract nature of on-screen code with real-world cause and effect. Block-based coding platforms that control robots work for ages 9 to 11. Kits like Lego Mindstorms or Vex Go kits use drag-and-drop block coding to program motors and sensors. Your child writes code on a tablet, uploads it, and watches the robot execute, reinforcing that code does something tangible. You'll need iOS or Android tablets or Windows or Mac OS computers. Most are offline capable once software is installed, but initial setup requires internet. Microcontroller starter kits with visual editors fit ages 10 to 11. The MicroBake Go bundle uses MakeCode, a block-based editor that compiles to actual microcontroller code. Your child drags blocks, but behind the scenes, the microbit is running real embedded code, preparing them for Arduino's text-based IDE without the syntax learning curve yet. You'll need a micro USB cable and AAA batteries for portable use. It runs offline once code is uploaded, and it's durable for classroom environments. Sensor-driven conditional programming works for ages 9 to 11. Kits with light, sound, or distance sensors teach event-driven programming. When button pressed, do X, or while distance is less than 10 centimeters, do Y. This introduces real-time decision-making in code, a leap from pre-planned sequences. Parallel processing and timing come in around ages 10 to 11. Block-based platforms that let your child run multiple scripts simultaneously, like Scratch's "when green flag clicked" across multiple sprites, teach concurrency, the idea that multiple processes can run at once. This concept is essential before Arduino, where managing timing without blocking code is a common challenge. Debugging with serial monitors and LED feedback also fits ages 10 to 11. Visual coding platforms often include real-time variable displays, or LED indicators. Your child learns to read debugging output, a critical skill for text-based programming, where print statements and serial monitors replace visual cues. By the end of this stage, your child should be able to write a multi-conditional program that responds to sensor input in real time, debug using output feedback, and explain how their code controls physical hardware. They're ready for text-based coding when block-based syntax feels limiting, when they want to do something the blocks don't support. You'll need a computer or tablet here. Specs vary by platform. Most run on Chromebooks or entry-level laptops. Check offline versus cloud-dependent functionality. Some platforms, like Scratch, default to online, but have offline editors. MakeCode works offline after initial download. You'll need USB for uploading code to hardware and Bluetooth for some robot kits. Look for kits with sensor packs and motor add-ons that grow with skills, rather than standalone closed systems. There's a robotics kit compatibility checklist in the resources that helps you verify software and hardware compatibility before purchasing. Now we get to the advanced stage, ages 11 and up. This is Arduino IDE and text-based embedded programming. This is the culmination of the progression. Your child moves from visual blocks to industry-standard text-based code. Arduino is where hobbyist skills meet professional ones, the same IDE and language, C++, used in robotics labs, engineering firms, and university courses. Arduino Uno R3 starter kits are the standard entry point for ages 11 and up. Check the link below for the Arduino Starter Kit official. It includes the Uno board, breadboard, LEDs, resistors, and a project book that teaches C++ syntax through hands-on builds. Your child writes code in the Arduino IDE. It's free, runs on Windows, Mac OS, or Linux, and fully offline capable, compiles it, and uploads via USB. You'll need a USB-A cable and 5-volt power from a computer or wall adapter. Breadboards and components are reusable across projects. Expect occasional wire failures and LED burnout, so factor in replacement packs. Transitioning from blocks to text works well for ages 11 to 12. Tools like Arduino or MBlock offer a block interface that generates Arduino C++ code in real time. Your child sees the text version of their blocks, making the syntax leap less jarring. This is a bridge, not a destination. Use it for 2 to 3 projects, then move to pure text. Sensor integration and analog input come in around age 12 and up. Arduino projects with potentiometers, photoresistors, and temperature sensors teach analog to digital conversion and real-world data input. Your child learns to read datasheets, calculate resistor values, and write code that interprets noisy sensor data, practical engineering skills that screen-only code can't teach. Libraries and code reuse also start around age 12 and up. Arduino's ecosystem of community libraries for servos, displays, sensors teaches your child to read documentation, import dependencies, and build on others' work, mirroring professional software development. This is where coding becomes a collaborative, real-world skill. Debugging embedded systems is a big leap, also around age 12 and up. Arduino has no interactive debugger. Your child uses serial print statements to trace variable values and logic flow, teaching the fundamentals of debugging without IDE guardrails. This is harder than block-based platforms, and that's the point. Frustration tolerance built here pays off in every future programming language. Expanding to Arduino Nano, ESP32, and Raspberry Pi Pico fits ages 13 and up. Once the Uno feels mastered, microcontroller diversity teaches that C++ skills transfer across platforms. The ESP32 adds Wi-Fi and Bluetooth. The Pico uses MicroPython. Your child learns that programming isn't device-specific, it's about understanding hardware interfaces and adapting code. By the end of this stage, your child should be able to write, compile, and debug original Arduino projects from scratch, read component datasheets to wire circuits independently, and modify library code to suit their needs. These are entry-level embedded engineering skills, the same ones used in IoT development, robotics startups, and university mechatronics programs. Arduino IDE requires minimal system resources. It runs on old laptops. Power requirements are 5 volts USB or 7 to 12 volts barrel jack for standalone operation. Connectivity is USB for programming, optional Bluetooth or Wi-Fi with advanced boards. For safety, soldering irons for permanent projects require ventilation and adult supervision until around age 14. Expandability is infinite. Arduino is an open platform with thousands of compatible sensors, actuators, and shields. Boards can survive shorts and miswiring to a point, but static discharge kills them. Invest in anti-static wristbands for dry climates. For more on Arduino-compatible robotics platforms, check out the best Arduino robotics kits for kids in the resources. Let's talk about supporting infrastructure, lab setup, and continuity across stages. The progression only works if each stage builds on the last, and that requires intentional organization and progressive storage. You're not just buying products, you're curating a learning environment. Dedicated storage for each stage matters at all ages. Keep screen-free tactile tools in one bin, block-based hardware in another, and Arduino components in labeled drawers. When your child revisits earlier stages, and they will, skills aren't linear, retrieval should be effortless. Clear bins with picture labels work for younger kids. Drawer organizers with component labels like resistors, LEDs, sensors work for teens. Documentation and project journals start around age 6. Encourage your child to photograph or sketch each completed project and note what worked or didn't. This isn't busy work, it's teaching version control and iterative design. By the Arduino stage, they should be keeping a lab notebook with circuit diagrams and code snippets, mirroring professional engineering practice. Power and connectivity infrastructure becomes important at age 9 and up. Once you introduce hardware, you need reliable USB ports. Invest in a powered hub if using an old laptop. You'll need spare cables and a consistent workspace with good lighting. Flickering connections cause frustration that looks like coding failure, but is actually hardware failure. Don't let bad cables sabotage confidence. Expandability planning matters at all ages. Buy kits with open-ended expansion rather than closed ecosystems. A microbit or Arduino grows with your child through add-ons. A proprietary robot that only works with its app becomes e-waste when they outgrow it. Check compatibility with third-party sensors and components. Open platforms win long-term. Consumables budget becomes necessary at age 11 and up. Arduino projects burn through LEDs, resistors, and jumper wires. Budget for replacement components quarterly. This isn't product failure, it's the cost of iterative learning. A box of 100 LEDs costs around $8 and lasts months. Don't let a 10-cent burnt LED halt a project. Software version management starts at age 9. Block-based platforms update frequently, sometimes breaking old projects. Pin software versions when something works, or keep offline installers. Arduino IDE is stable, but library updates can introduce breaking changes. Teach your child to read changelogs and test before updating. For a complete guide to setting up a space that supports this progression, there's a How to Build a Home STEM Lab guide linked in the resources. Here's a quick reference checklist to verify your child's readiness for each stage. For the foundation stage, ages 3 to 6, your child should be able to follow multi-step verbal instructions independently, recognize patterns and repeating sequences in daily life, understand that actions have predictable outcomes, and show frustration tolerance when a sequence doesn't work as expected. For the intermediate stage, ages 6 to 9, they should create multi-step plans before acting, not just guess and check. They should explain reasoning for a sequence of steps, identify errors in their own or others' instructions, and understand that one action can represent multiple steps. For the transition stage, ages 9 to 11, they should be comfortable with symbolic representation. Icons and blocks feel intuitive. They should read and follow written instructions independently, troubleshoot using feedback like lights, sounds, or error messages, and express curiosity about how things work behind the interface. For the advanced stage, ages 11 and up, they need to tolerate delayed gratification. Debugging takes time and patience. They should read technical documentation with adult support, type comfortably enough that syntax entry isn't a physical barrier, and show intrinsic motivation to build original projects, not just follow tutorials. Now let's hit some frequently asked questions. How long should my child stay at each stage before moving forward? There's no fixed timeline. Readiness is skill-based, not age-based. Most children spend 6 to 18 months at the foundation stage, 12 to 24 months at the intermediate stage, and 6 to 12 months at the transition stage before feeling limited by block-based platforms. Watch for intrinsic frustration with current tools, not boredom, but "I want to do something this can't do," as the signal to advance. Rushing creates gaps. Staying too long creates disengagement. When your child completes projects independently at their current stage without adult prompting, they're ready to explore the next stage. Can my child skip screen-free stages and start directly with block-based coding or Arduino if they're older? You can, but you'll likely circle back to fill gaps. A 12-year-old starting Arduino without prior computational thinking will struggle not with syntax, but with algorithm design, the "how do I break this problem into steps" thinking that screen-free tools build viscerally. If your child is older but new to coding, spend 2 to 4 weeks with intermediate stage screen-free tools, not the preschool ones, to build debugging habits and sequencing intuition. Then accelerate through block-based platforms in a few weeks rather than months. The goal isn't to complete every product in every stage, it's to ensure the cognitive foundations exist before adding syntax complexity. What's the difference between screen-free coding and just playing with puzzles or games? The intentionality of computational thinking instruction. A jigsaw puzzle builds spatial reasoning, but it doesn't teach sequencing, conditionals, or debugging, the core structures of code. Screen-free coding tools are designed with explicit parallels to programming concepts, loops, functions, branching logic. When you use them, you're naming those concepts aloud. Look, you created a loop. This part repeats. You're connecting tactile actions to future text-based syntax. Play is the vehicle, but the learning outcome is specific. Generic problem-solving toys are valuable, but they won't accelerate the transition to Arduino the way purpose-built coding tools will. The progression isn't about delaying screens. It's about building foundations that make screens productive when they do arrive. Each stage in this checklist develops specific cognitive skills that transfer directly to text-based programming, robotics, and eventually software engineering. Your child doesn't need to master every product at every stage. They need to develop the thinking patterns each stage represents: sequencing, abstraction, debugging, hardware control, and finally, text-based syntax. Some kids race through in 2 years, others take 5. Both paths are valid. When your 13-year-old writes their first Arduino sketch that reads a sensor and makes a decision in real time, you'll see the through line from the preschool robot mouse they programmed with arrow buttons to the C++ for loop blinking an LED. That's not luck. That's progressive skill building, one tactile step at a time. That wraps up this episode of the STEM Lab podcast. Thanks for listening all the way through. New episodes come out every Monday, Wednesday, and Friday, so you'll have fresh content waiting for you regularly. If this episode was helpful, I'd really appreciate it if you could leave a 5-star rating and write a quick review. It actually makes a huge difference in helping other parents discover the show when they're searching for this kind of practical guidance. And make sure you're subscribed or following the show so you get notified the second a new episode drops. See you next time.